Question 9, quite a tricky question this. It's about vanadium compounds and ions. Use the table 4 to identify species that can be used to reduce VO2+. There's VO2+ at the top with an electrode potential of 1. Used to reduce VO2+ ions to VO2+. Yeah, that's the top one. Electrode potential 1. And no further. So first of all, you've got to decide which of the other equations could make this reaction happen, this top one, with an electrode potential of 1. Well, if this one's going to go ahead in this direction and have a positive electrode potential of 1, the other ones combining with it would go the other direction. Yeah. So there's electrons on this side, on the left-hand side of this one. This is reduction. These would have to be turned into oxidation and go the other way around, and these figures would become minuses, or this one will become plus. So this one, and say for example this Cl2 plus 2 electrons 2 Cl minus, would be plus 1 for this one in this direction, reduction, and this one will be forced into oxidation, minus 1.36. Plus 1 minus 1.36 is minus 0.36, so that wouldn't go ahead. So it can't be this one. In other words, you're looking for something with an electrode potential lower than 1. All the others could feasibly work, but Cl2 plus 2 electrons to 2 Cl minus will not combine with that top equation and make that top equation go in that direction, so that VO2 plus is reduced. All of the others would do, because if we make all the others minuses, or this one minus minus a plus, when we add these on, this overall 1.00 is bigger than, say for example, plus 0.77. So this one could go in the other direction, minus 0.77, add 1, still gives plus 0.23. It's still a positive value, and this one would go ahead. Okay, but the question is, which of the others is it? Okay, it says and no further, and no further. So when you make VO2 plus here, it could react again. VO2 plus 2H plus an electron goes to V3 plus an H2O. It could do this one. So we want this one to go ahead with an electrode potential of 1, but this one not to then go ahead with an electrode potential of plus 0.34. Your answer is Fe3 plus an electron goes to Fe2 plus. This is your equation here. That one will do it. Let me explain why. Plus 0.77, we're going to force it to go in the backward direction, so it becomes oxidized rather than reduced. So this one can go in the forward direction. Plus 1, take away 0.77 gives plus 0.23. So this one goes ahead. Will this second one go ahead? Plus 0.34 minus 0.77 gives a minus value, because this is bigger than this one. So the second one wouldn't go ahead. This one wouldn't be reversed and go in, wouldn't be an oxidation reaction. It wouldn't go right to left. It would continue to go left to right, because otherwise, if this one went ahead and this one went backwards, it would give a negative electrode potential. Okay. So my answer is the reagent that can be used is Fe2 plus. That can be turned round and make Fe3 plus, because the electrode potential of VO2 plus is 1. The electrode potential of VO2 plus is plus 0.34. And the electrode potential of Fe3 plus to Fe2 plus is 0.77. It's less than 1, 0.77. So if you combine those two, 1 take away 0.77 is 0.23. So this top one goes ahead. But it's larger than plus 0.34. 0.77 is larger than plus 0.34. So if you reverse it around the other way and it becomes minus 0.77 plus 0.34, you're going to get a minus 0.43. And that's not going to go ahead. Question 9.2. Give the oxidation state of vanadium in VOH2O6 2+. Well, the waters are neutral. The O is minus 2 oxidation state because it's in group 6, going to gain 2 electrons to fill its outer shell, minus 2 charge, minus 2 oxidation state. So something, an oxidation state of the V, minus 2 gives plus 2 overall. So your answer is 4, because 4 minus 2 is plus 2. This VH2O4 Cl2 plus ion has 2 isomers. One isomer is shown. Draw the structure of the other isomer and state its type of isomerism. Well, what we've got is, we've actually got geometric isomerism here. We've got here the 2 Cl's with a bond angle of 90. They are together on the same side. Z isomers. However, if they were opposite, either there and there, or here and here, they would be opposite each other and have a bond angle of 180. So this way, they are Z isomers opposite each other, either there and there, or here and here, or even here and here. They will be opposite and they will be E isomers. So I've drawn another one with 2 Cl's opposite. Now I've moved the Cl from here to here, so they're opposite. You could have had the Cl up and down as well, either way you wanted to, as long as they're opposite. And the type of isomerism is geometric isomerism. You can also call it cis-trans or EZ, or even just say it's stereoisomerism. Stereoisomerism means that you've got the same structural formula but different positions of atoms in space. It also includes optical isomerism. Heating VH4VO3 produces vanadium 5 oxide, water and another product. Well, we need to decide what V5 oxide is. Vanadium is an oxidation state plus 5. Oxygen, O, is an oxidation state minus 2 because it's in group 6, going to gain 2 electrons. So I've got a 5 oxidation state and a 2 oxidation state. So let me do spoilers and show you what vanadium 5 oxide is, and you'll understand. It says here NH4VO3 makes, this is vanadium 5 oxide. Let me explain how I've come up with that then. We said oxide, the O is minus 2 oxidation state. The V is in 5 oxidation state. So we've got to get those two to balance to have no charge left over. 2 5s are 10, 5 minus 2s are 10. So 2 plus 5s gives plus 10 oxidation state here. 5 minus 2s gives minus 10 oxidation state and leaves no charge left over. It also says it makes water, and then you've got to work out what you've got left. Well, you've got some N's that you've not used, and you've got some H's that you've not got used, so it makes ammonia. Okay, you probably have to work that out, something with N's and H's in it, and then you can balance it. You're going to need 2 V's, so you're going to need 2 in front of the NH4VO3. That means you're going to need 2 N's or 2 NH3s to balance it up. Vanadium 5 oxide is the catalyst used in the manufacture of sulfur trioxide, SO3. Give 2 equations to show how the catalyst is used and regenerated. So we use V2O5 is used in the manufacture of sulfur trioxide from SO2. So sulfur dioxide makes sulfur trioxide, V2O5. The only other oxidation state that we know of as an oxide is vanadium 4. 4 minus 2s for the oxygens, minus 2 oxidation state for NO, remember, because it's in group 6, gains 2 electrons, 2 minus charge, so 4 minus 2s is minus 8. So 2 4s, that's in oxidation state, plus 4, 2 Vs. So that's vanadium 4 oxide. Now then, this V2O4, it says the catalyst is regenerated. The vanadium 5 oxide is regenerated. So it's going to be remade from V2O4, which is made. So the V2O4 reacts with more oxygen to remake the V2O5.